I am super excited to be here today. This is my first time at Utah.js, but I have been to the Salt Lake City area many times for many conferences, two Remix comps, two Epic Webs, a React rally, and it's fantastic every time. I love meeting people here. I've made some lifelong friends through these events, so I'm hoping to make some more today. I'm here to talk about leveraging web APIs to build portable, universal JavaScript libraries. This idea came to me as I work at Prisma, and we build a lot on Cloudflare workers. And historically, Cloudflare workers, they run JavaScript, but they're not Node. And a couple years ago, that made it kind of difficult to adopt certain packages off of NPM because they would have Node dependencies, right? Over the last 2 years, Cloudflare has polyfilled in a lot of this behavior, so that's not as much of a problem. But it did get me thinking about why the ecosystem hasn't really adopted some of these built-in things that can solve the same problems, and it's sort of holding that evolution back. So we're going to talk a little bit about that. So first, there are more runtimes than Node.js, right? Many of them that you may or may not be aware of. We talked about just Cloudflare workers. That is running on V8, which is the same JavaScript engine that powers Chrome and Node, but it is not Node, notably different. We also have Deno, which is also V8, but also not Node, and started to build in some Node APIs more recently. We have Bun, which is completely different. It's running JavaScript core, which is like Safari's engine, but it does implement a lot of Node APIs for compatibility purposes. There's Hermes, which is for React Native, which is totally different than everything else. But the important thing is that all of these are JavaScript, and there is a standard set of like functionality that's expected to work there. Many others that we could get into, those are just some of the notable ones. But what's really interesting is that many of them have started filling in Node APIs just to meet the industry, like where it's at in the package ecosystem. That's great for adoption, but it does bring in these like bundle size increases from polyfilling things in, maybe some performance overhead. Necessary for adoption, but it also to me feels a bit like it's holding the ecosystem back from like pushing forward into the APIs we have available today. And then the browser is also becoming a development environment. If you've seen things like V0, Lovable, Bolt, people are able to, that had no like tech experience before, are building apps in these systems that are running fully in the browser. And what I think is really cool is that the browser is a perfect sandbox for these like single-use individual apps that are being built. It's isolated from all the host machine. You can't go in and like screw up your file system with it by accident. It's just a great environment, but there's some challenges there that we have an ecosystem of packages that can't run there because they're dependent on these like node-specific libraries. We want our packages that we ship to be able to run in these new modern runtimes, mainly the browser. And if I haven't convinced you yet, this is a chart of downloads for a package called unenv. Unenv's sole purpose is to polyfill Node APIs in runtimes that don't support them. And over the last 12 months, the number of downloads from August of last year to this year is 2.5 times what it was. So it's like a 150% increase in growth. And I'd be surprised if you're familiar with this package because most people never interact with it directly. It's something that maybe a framework pulls in, or like Cloudflare will pull it in for you if you're using Wrangler. So it's kind of like something lower level that patches in this compatibility layer for you. But the fact that it's grown by that, and NPM numbers are kind of weird. It's not like a great basis for a lot of judgment. But I do think it shows a trend that there's a lot more usage of environments. Because if you're running Node, you're not going to use this at all, right? So the fact that this has grown so much means that there's a demand for adopting these like Node packages and imports into non-Node runtimes. OK, finally an intro of me. I'm Tyler Benfield. I'm a staff software engineer at Prisma. I work primarily on Prisma Postgres, which is our hosted Postgres offering. But I've been doing web development, application development for getting nearly 15 years now, mostly in the web space. I definitely gravitate towards database type technologies, even early in my career. And I love talking about that kind of stuff. So you'll often find me talking about performance, tuning databases, how to get more out of them as an application developer perspective. But I also learn a lot of things at some of the lower level of the stack from doing this that I like to share too. And that's what today's all about. So for today's agenda, I've got a QR code here for the repo that has all of these slides, some benchmark examples, cool stuff. If you want to check that out, you're welcome to. I can also pull it back up at the end if you're interested. But we're going to try to hit a few things. There was so much I wanted to get into this talk, and I ended up writing some stuff and then having to cut it all back down because it was just too much. So we're going to focus on some things that I think are the most high-value takeaways today. And then we'll tease some stuff towards the end. All of these APIs we'll look at are available to use in Node.js today. They run in all browsers today. Like, you can start using them as you leave this room. Some of them have actually been around for quite a while. I'm not talking about a lot of like brand new stuff today. There's a talk later in the day that's all about that, and I'm really excited to see that one. But this is about stuff that's actually existing. We're just not leveraging it in the packages we ship. Okay, so first we're going to talk about binary data and how to work with it without Node buffer. We're going to talk about streaming without using Node streams. And we're going to talk about doing crypto work without using Node crypto. All this stuff built into the browser and the web now. So let's start with binary data. Why would you need this? If you're working with wire protocols, like I work with Postgres and MySQL protocols a lot at like a lower level, you're probably dealing with like binary data moving across the wire. If you're building packages that are consuming file formats, like maybe you're uploading an image or an audio file, probably working with binary data there. Any kind of like encoding or decoding of data that's not in like a text representation, you're going to come across this. The lowest level of all of it is array buffer. So this is a sort of pointer to a generic representation of some data in memory, a linear representation of that data. So I can say I want an array buffer of 1 kilobyte. The browser's going to give me, or the web APIs are going to give me 1 kilobyte of linear data in memory to work with. But it's very unopinionated about what data goes into that array buffer. It has no idea. Array buffers can be transferred and clonable. So if you're working with service workers, web workers, you can move data between them. It also has zero copy slicing, which is really cool. That's where we can take a 1 kilobyte of data and say, I only care about like this 500 bytes in the middle, slice that out and hand it to something else without copying it. They can also be resized, but resizing is kind of weird because it has to be linear memory. So if you're going up from 1 kilobyte to 2 kilobyte, for example, that next segment of memory might not be available. So it has to allocate a whole new allocation for that. So be careful with resizing it there. But notably, array buffer doesn't give us any way to access the data inside of the buffer. And that's where typed arrays come in. Typed arrays give us a view into the data inside of that memory under a particular lens. You can have multiple views of the same data even. The most common one is uint8 array. That's like a true like byte representation of this data. You get numbers back from it in the range of like 0 to 255 like you would expect from bytes, and you can manipulate them directly. But we also have some specialized views. You have other uint versions. There's ints, floats, big ints. These are all, they kind of like look at multiple bytes at a time to form these data types and representations. But they can all look at the same array buffer instance underneath. They're more useful in things like graphics rendering, audio processing, maybe doing simulation data. You might have some of these more advanced numeric types. But usually we're going to uint8 array for most stuff. They also give you all the normal array functions you might expect. You can map, reduce, filter over the values in the arrays. But you have to be careful because these arrays can be very large, right? You're handling binary data, so they could be hundreds of thousands of values. So for reasons like if you call subarray on it, that's actually going to do a copy of that data versus slicing it that's going to be a representation of the same data. There's nuance like that to be aware of when you're working with this like sort of quantity of values. Okay, that's really cool. But then there's data view, which I think is like awesome and so underutilized. It gives you a way to work with mixed representations of data in the same array buffer. So you pass it the array buffer instance, and you get getters and setters for uints, ints, floats, big ints. You can use them sort of interchangeably over the same data set. So on the right here, you can see I've got a buffer that I'm encoding in the geographic coordinates of Sandy, Utah, and the date of the conference with mixed sort of data types in there. I'm able to pack that data down very tightly. And if you can imagine like hundreds of thousands of these entries like you might store in, say, a database or a compact file, this is going to become very valuable, right? Versus something like JSON encoding that's going to bloat a lot of the file format. Now, data view notably doesn't give you anything for working with text, and you probably want to work with text. So that's why the web APIs give us text encoder and text decoder. They're built-in ways to handle UTF-8. Pretty self-explanatory there, right? There is one interesting thing, though, that there is an encode into. So again, like trying to avoid copying memory as much as you can either call encode to get handed the string and get back the uint8 array representation of that, or you can give it an array buffer and say, write it into this buffer that I already have. So you don't have to copy it yet again, like between memory. But these are all like really good primitives, but I don't find them very ergonomic to work with all around my app code. It's kind of too low level for that. So what I like to do is write a sort of class wrapper to do a reader or writer on top of these that is opinionated about the data I'm working with. So I might have a reader class here that takes in an array buffer in its constructor, and then it gives me something like a read string, where I can just say, this is how many, the length of the string I'm expecting in this case. And it's going to do the decoding for me. And it also conveniently tracks my position in that buffer, so I don't have to do that offset management myself. And then you can use it like I've got on the right here with like reading bytes, reading strings. You could also do things like read a lat long value, read a date, read a timestamp, whatever makes sense for the data you're working with. And you can do the same thing for writing data too. OK, that's really cool. What's the trade-off? Because there's got to be a trade-off. Hex and base 64 encoding are not native yet. We have a stage 3 proposal, so it's on the way. But in the meantime, you have to write your own utility functions or import some in to do that for you. We also don't have immutable array buffers yet. That's a stage 2.7 proposal, which I learned recently exists. And actually, node buffers don't have this either, but it would be really valuable for us to have this because then we can handle, pass a slice of an array buffer to some function that we don't expect to manipulate it. And also, kind of annoyingly, there's no concatenation of array buffers. You can't like join them together. Kind of annoying limitation, and there's kind of a dead proposal for that, which is unfortunate. Buffer concat in Node solves this, right? But interestingly, I learned through doing this that buffer concat is not zero copy either. It actually will allocate, if you give it a handful of buffer instances, it'll allocate memory equal to the total size of that, and then move it all over there. So it's actually not that efficient to do it either. And in fact, in my performance benchmarking, and this is not a talk about performance benchmarks, there's tons of nuance to it. I've got the benchmark scripts in the repo if you want to try it yourself. This is just the numbers that I got on a couple quick passes of it, right? My implementation of the buffer concatenation with UN8 array is actually 1.2 times faster than buffer is, just trying to follow the exact same semantics that it does. UN8 read-write between data view and buffer, pretty much equivalent, doesn't matter the difference. Encoding is a little bit slower though. The best effort I could get on like hex and base 64 encoding is about 6 times slower than node buffer. But again, like we're talking on the order of like microseconds here. This is probably going to be irrelevant for your app either way. But it is interesting if you're in like a really performance critical situation. I'm curious to see when we get native base 64 and hex in the browser, what that's going to look like, or in the web APIs, I should say. And then text decoder, very equivalent to buffer, no overhead there. So I would strongly encourage you to use these. I think the performance differences are pretty negligible here in the grand scheme of things. But benchmark it yourself and see what you think. It can vary with like the size of data. OK, let's move on to some streaming. So the web APIs give us native ways to do streaming. The first is readable stream. This lets us map an arbitrary like source of data that's going to like emit stuff to us into a stream that we can build pipelines off of. And what's really cool about the web stream APIs is this idea of back pressure. So this lets us significantly reduce our memory consumption as we're consuming data. Essentially, the consumer, the writable side, the end result, is defining how fast we're going to pipe data through this stream. And it does so by asking for it instead of us pushing it to it. So when it's ready for data, it's going to ask, it's going to funnel all the way back up to this readable stream and call this pull function you see on the right. What we do in that pull function is up to us. If we want to grab data from some other source, we can do that asynchronously. It supports promises here. We grab that data, we enqueue it with this controller.enqueue, and then that makes it available downstream. Interestingly, we can also do things like if it's more efficient to grab multiple values at the same time, that's totally fine. We can enqueue multiple values here at once. The streams handle all of that sort of situation for us. And then when we're done, when the readable source is done, we can call controller.close. This handles the back pressure from start to finish for us so that we never bring everything into memory all at once. We're bringing data in as fast as the consumer can process it. Super cool functionality there, and very simple to take advantage of. If we do have a data source that doesn't really support this pool model, though, there is another lifecycle method you can use in the constructor called start, and then you can attach like listeners and stuff and enqueue data that way. So you do have a safety net there, but you have to be careful that that could accidentally queue up more data than your consumer, your writable side can handle. Right? Speaking of the writable side, this is what the writable end looks like. You have a writable stream constructor. You give it a write function. That write function takes a single value and does something cool with it. You can push it to a file, send it to some other API or something, wherever you want to go. This can also be asynchronous and return a promise. And that's what really ultimately controls that back pressure. As long as that promise is still pending, it's not going to pull more data off of the readable side until it's ready. You can configure it to optimistically pull some stuff, but that's totally up to you if you want to do that. and take that into memory consideration, right? And then we have transform streams. These sit in the middle and let us manipulate the data as it goes through. And the simple example of that is, hey, I want to take like this number value and multiply it by 2, so double it every time it comes through. Pretty simple transformation, right? Like easy. But we can do really cool stuff with transform streams that is maybe not as immediately obvious because it gives us the value and the controller. We're not just returning the new value, we're having to call controller.enqueue on it. The reason for that is we can do more than just enqueue a transformed value. For example, we can have a filter in this and say, I only want to emit the value downstream if it is an even number. And then I conditionally call the enqueue function. What this will end up doing is if I don't enqueue a value from this transform stream, the writer side is still waiting on a new value, so it's going to go back to the reader and pull another one. So until my transform lets another value through, it's going to keep reading one at a time off that readable side. Again, like keeping memory super low while letting me build these pipelines up. I can also emit multiple values out of a transform stream from a single input. So if I want to take, for example, like a paragraph of words and split that and enqueue individual words downstream, something I can easily do here. When you put it all together, you have these like pipeline sort of syntax to it. There's a pipe through function on the readable side that you can pass a transform stream into. You can chain those together to do multiple pipe throughs, go through isolated transform streams that are, it's really cool because you can build these like single responsibility transform streams that do like small pieces of work and build a full pipeline and compose them in different ways. And then when you get to the end, you can call pipe to and send it to a writable stream. The pipe to is going to return a promise. That promise will resolve whenever the stream ends. So that could also be indefinitely, right? Like the stream might be constantly producing results, and it will reject if the stream has any kind of error to it, right? So here on the right, I've got an example of maybe we read data out of a file. We pipe it through an uppercase stream. So every chunk out of that gets converted to uppercase and then written to a destination file. That input file could be many gigabytes, but we're going to have very little memory usage of this because we're only processing one chunk at a time through our memory and out to the other file. Maybe a more modern example is LLMs do streaming responses now. So maybe we have a function to go send some prompt to an LLM. It gets us back starts streaming the text to us, and that text is probably going to contain some markdown that we want to show to our users, right? So we pipe that through like a markdown processor and have that emit some type of object representation that we can handle pass to like a sink that does the rendering of that markdown, right? So this lets us incrementally process that markdown and give it to the user as it comes through with like 3 lines of code, whatever the underlying implementation looks like. Performance, again, this is like microsecond level benchmarks. Keep that in mind. If you just construct a web stream compared to a node stream and emit one value through it, web streams are like 5 times faster in my test. However, once you put like 10,000 values through, it's like 10 to 15 times slower. So node streams definitely have an advantage on the event processing side, where web streams are pretty good at the like initial construction, right? Again, this is like microseconds per event, and most streams are bound by I/O, not by CPU. In my case, I'm just producing numbers out of there, so it's not really a good representation of where you would actually use streams. I don't think this is going to matter in reality, right? And the reason for some of this overhead also comes from web streams does all this back pressure management. Node streams don't. It's much harder to do that yourself. That comes with state management inside the streams, a lot of like async work and tracking of state machines. That has overhead. So we get the advantage of back pressure in this nice API at the cost of a little bit of performance on like the microsecond level. Okay, let's move into some crypto stuff. We get 2 really useful utilities straight out the gate on crypto. One is random UUID. It gives us a version for UUID, pretty self-explanatory, but it comes from a cryptographically secure source of randomness. So this is the platform giving us a, sometimes like, whatever the OS level can give us as a good implementation of the crypto randomness. Kind of delegating all of that down to the runtime to do. That's a good source for like unique identifiers, single-use tokens, codes, like if you're doing password reset emails, stuff like that. This function just exists. You don't need a package to do that. In other cases where you need arbitrary numbers of values, you have get random values. You can give this a typed array like what we saw earlier. Could be a UN8 array, could be a float array. Just depends on what kind of data type you want. Give it to get random values. It's going to populate that whole array with random stuff. This is super useful if you need initialization vectors for other crypto functions. You need password salts. You need to seed other random data. You want to generate something ahead of time and then use that as a seed. Or just any kind of unbiased random number generation, much more reliable than like math.random. Then we have subtle crypto. This is a set of functions that you can use for general like crypto purposes, I guess, like a variety of cases. We have hashing. We can use digest for that. We can do like SHA-256 hashes. I forget all the variants we have, but there's a lot of options that exist. Encryption, you got encrypt and decrypt. You can do right in the web APIs. Also signature verification of data. And what's cool is you can also generate keys for this. So you can have scripts that generate a key that can be used for encryption, all within what is built into the web APIs now. A few examples of those on the right. The reason it's called subtle crypto is because there is a lot of subtle details to this to get right. If you look at the docs, they can be a little bit intimidating with the number of options you get, but they are really good. And honestly, like once you kind of pursue it, the hardest choice is what algorithm you should use and some of the key length stuff, right? If you kind of understand that bit to it or look into that, the APIs themselves are super easy to use. But that said, you might want to use something a little bit higher level in your app code, right? But this is really useful if you're doing things like you're going to write a package that does JWT signature verification. Well, instead of like using Node crypto, you should just use this. But then as an app developer, you probably want to use that JWT package that's hardened for that, right? OK, I am going to start wrapping up here. Like I said earlier, there's a lot of things I had to cut for time that I wanted to dive deep into. One is the temporal spec. This is in stage 3 right now from TC39, but it is super cool. It's a pretty big spec, but it fixes dates in JavaScript by giving us really good date, time, duration, date math, formatting, everything. Yeah, that deserves some applause, right? Do a whole talk on this one. It is fantastic. Still on the way, but very, very close. The spec is really good. There's some polyfills out there that give you some good implementations to start trying out. If you're a library author, I would say start considering if you have dates as inputs, try to see if you can accept the temporal types in place of this. Don't rely on it. Don't put that burden on like consumers yet, but give the option that consumers could pass a temporal type into your code and do the date conversions yourself, right? That way you future-proof for this API that's coming, and it's going to be great for your users to be able to just start passing temporal. And you can also be much more explicit about like, I don't just want a JavaScript date that is not very representative of like I only want the time portion or something. You can be very explicit with temporal. Then there's explicit resource management. No more try-finally nesting many layers deep. If you have to do like cleanup functions to part of your code, like if you have database connections and you need to close those at the end of the context, this is for you. If you're a library author, oh, and we also get a new keyword with this, which is rare and cool. There's a new using keyword in JavaScript that takes advantage of this to replace the whole try-finally nonsense. If you're a library author, I would encourage you to start looking at implementing the symbol.dispose and symbol.async dispose that power this. You can do that in a pretty non-invasive way in the code that you have and make it sort of future-proof to this use case that's coming. Then we have iterator helpers, which are now available in all browsers and Node 22. It gives us the ability to work with iterators similar to how we work with Node APIs, or sorry, array APIs. You can do like map, reduce, filter over iterables, which is great because usually we get lazy and we just take an iterable and inflate it into an array, and then that buffers everything to memory. Or we're stuck writing these like messy for loops with doing all the like, we can't do the nice new like map and reduce filter APIs. Now we have that with iterators. Then there's INTL. This one is not utilized as much as I would like to see. It's super cool. You can do date, time, number formatting directly in the browser or in the server-side runtimes with localization support too. You don't need libraries to do all of this. It's been widely available since 2017. Super stable, ready to use. You don't need libraries to do any of your date formatting. And what's really cool about it is it's more declarative. So you can say the sort of structure of the date that you want to represent, or the number you can say, I want it to be currency of this type. And it determines how to show that to the user based off their localization preferences, which is super cool. Then we have async generators. These could use a whole talk, but they are good ways to model state machines and yield control to the callers. It's really hard to condense that down into a few words, so go look at the examples. It is super cool though. You can like have a function that ejects back out and lets the caller decide when to proceed and provides value back into the middle of the function to keep going. And then we have proxy and reflect, which let us intercept calls into functions or object methods, even like property access, and do creative stuff with it. For example, you could maybe do like tracing or logging around function calls without like having to override or overload the function itself on the object. That's been in the Web API since 2016. And all of these come from the TC39 technical committee that does all the specifications for ECMAScript and JavaScript. Okay, some takeaway actions here. As an application developer, I want you to just do what works for you. A lot of this like compatibility stuff and universal concepts, if you're always building in Node, I don't expect that you're going to be jumping between Node, Deno, Cloudflare Workers, Bun all the time, right? You got better things to do, better things to build for your users. It's no problem if you keep on the Node APIs necessarily. But consider if you're doing something like a server-side rendering framework like Next.js or React Router, you might be sharing code from your backend and your front end. And one day you pull this function, this utility function into your client components, and it doesn't work because it has a bunch of expectations of Node. So that's some incentive to like start adopting these APIs, but I wouldn't say go rewrite your whole app to get rid of Node imports. That's not necessary. But if you're a library author, then the burden is really on you. Please start adopting these new APIs. Stop relying on things like Node Buffer and Node Streams. When you can't, provide the runtime-specific exports. If you haven't seen that, come find me. I can show you some examples. It's super cool. You can give implementations that apply to specific runtimes when the package is imported. Also, please document which runtimes you officially support. There's more than Node now, and we do need to be explicit if there's a certain one that we're targeting. I can't tell you how frustrating it was when I was getting started with Cloudflare Workers a couple years ago, and I would grab a package only to find out it didn't work. I would have to dig into the source code to see, well, why doesn't it work? And then find out like whether I could actually patch it to be used or not. So be explicit there. And finally, there is this Web Interop Technical Committee, WinterTC. It's a group of representatives from all these different runtimes that come together and they help ratify these like changes to the specification, even now going beyond what browsers support, right? We're starting to look at what things that make sense in a server runtime, but in an interoperable level across. So like things like how do you attach a web server to a port in the same way across all the runtimes. So they're doing some really amazing work and they have some cool proposals coming. All right, that is all I had. My challenge to you is to build for the universe of apps yet to come. We're going to see a wave of AI-generated apps that run in the browser, and I want to see all of your packages run there. So thank you for your time. I hope to see you around the conference. Have a great rest of your day.